Hello everyone, myself Jianusha, working as lecturer in physics at SS Government Polytechnic, Zahirabad, and I am working in general section under the Department of Technical Education, Telangana, and I am teaching for first year, second sem students. The subject is applied physics with the subject code 18 common 203F. And the topic what we were discussing is fifth chapter from our syllabus, that is electricity and measuring instruments. And in today's session we are going to learn about meter bridge with the help of a small PowerPoint presentation here. The main objective of our class is, on completion of this period, you would be able to understand what is meter bridge and its importance, and how we can measure an unknown resistance with the help of meter bridge, and also we can measure specific resistance. Now let us recall what we learned in the previous session, that is recap for our class. In the last period we studied about Wheatstone bridge. So there we have seen the balancing condition of Wheatstone bridge. Now here you can see meter bridge, which is simply application of Wheatstone bridge. Now here you can see the same circuit which is designed in practical way and theoretical way. On left hand side you can see theoretical circuit. Let me explain what is practical circuit of meter bridge. Now you can see L-shaped metal bars which are placed such a way that it is forming two gaps. Now at both the gaps we are connecting, at one gap we are connecting one resistor, and at another gap we are connecting resistance box. Now you can see, as it is like Wheatstone bridge, where we are having A, B, C, D. AC is connected. Okay, here AB EMF and CD is connected with galvanometer. Similarly, in practical circuit, AB is connected with the battery, and C and D points are connected with galvanometer. Now, why it is called as meter bridge? Because here we are using a wire of length 1 meter, which is placed near to a 1 meter scale, which is simply 100 centimeter. Now at galvanometer we are using a device jockey. With the help of this jockey we can see the current which is passing through this 1 meter wire. Now as we all know that at balancing condition of Wheatstone bridge there is no current passing through galvanometer. So we need to find this balancing point at which there is no current passing through the galvanometer. So we move jockey on this wire which is placed between A and B. As we are moving this jockey on the wire, at some point the galvanometer shows no deflection. That means the bridge is balanced. So we consider this point as D. From A to D we call it as balancing length. You can see in the diagram we have taken two lengths, L1 and L2. So let us move on to the diagram here. The meter bridge consists of a resistance wire AB, which is of uniform cross section of length 1 meter. The wire AB is connected between L shape of copper or brass metal strips. These strips are M and N, which are fixed on wooden board. Now, when we place these metal strips, they're forming two gaps with the help of another metal strip C. Now, a meter scale is fixed parallel to the meter bridge wire. Now, when a battery and a plug key are connected in series between the ends of bridge wire, between C and jockey D, a high resistance and galvanometer connected in series. Now, the unknown resistance X in the front gap, a resistance RB is connected in the second gap. Okay, it is first gap. Now you can see in the picture that gap is we are indicating it with DF. So at this gap we are placing an unknown resistance X, and at second gap, that is at HK, we connected one resistance box. Now the jockey J is pressed at the two ends of wire on the bridge. If the deflections are in the opposite directions, then connections are correctly made. Now if deflections are not opposite, adjust resistance in the resistance box such that deflections are opposite when jockey J is pressed at the two ends of wire. Now the jockey J is pressed along the length of wire AB. At one position the deflection becomes 0. So this is what I just explained. Now this point is called as balancing point or null point. Now then high resistance is disconnected and exact balancing point D is located. Now the length AD, we consider it as L1, and the other length DB, that is L2, which is simply 100 minus L1. Now resistance R in the resistance box is noted. Now resistance box is nothing but the resistors which are connected in series, a number of resistors which are connected in series. That means we know the resistance which is present in resistance box. So using Wheatstone bridge condition, that is P by Q equals to R by S. In place of P, we are having unknown resistance X. In place of Q, we are having resistance box resistance. We are considering it as R. And the other two resistances, we are considering length of the wire, because as we know that resistance is directly proportional to length. In place of resistance, we are measuring length of the wire. So by using this formula, we can measure what is unknown resistance. So this experiment is repeated for different values of R in resistance box so that we can measure X value, and average value of X is the resistance of the conductor. So this is the tabular form, we can use it. So serial number, resistances in left side gap, balancing length of the wire, and the formula for X is equals to R into L1 by L2. Now how we can measure specific resistance? The length of the wire is measured, and we are calculating the value of resistance, and we can find the radius of the wire. By using screw gauge, we can measure the radius. So the specific resistance is calculated using the formula pi r square into X by L. So while doing this experiment, we need to take some precautions. This jockey should not be dragged on the wire. Contact should be made point to point. Very important precaution. High resistance should be disconnected near the balancing point. Current should be passed in the circuit only while taking reading. So when we are not taking reading, we can switch off the battery, or else we can open the key which is connected at the battery. So what we discussed in this session, we discussed about how we can construct a meter bridge and what is the experimental procedure of meter bridge to find resistance and specific resistance of the given wire. So the principle of meter bridge is law of conservation of energy, or simply it is meter bridge or Wheatstone bridge or none of the above. It is meter bridge. The resistance in the left gap of a meter bridge is heated. The balancing point shift towards right gap, left gap, no change and fluctuations. It shifts towards right gap. Resistance of wire depends on length, area of cross section equal to wire and indirectly proportional to length. It is directly proportional to length. Deflections in the galvanometer are when meter bridge connections are correct. Null deflection, one direction, opposite directions, none of the above. When all connections are correct, deflections in the galvanometer are in opposite direction. The balancing point of meter bridge is 40 centimeter. The ratio of the resistance in the left gap to right gap is 1:1, 2:3, 3:2, or 40:50. So you can see the balancing point is 40, the other length is 100 minus 40, that is 60. So 40 by 60, so we get the ratio as 2:3. Now, formula for calculating specific resistance S of a wire of length L, radius R and resistance X is pi r square L by A, pi r square A by L, pi r square X by L. It is pi r square X by L. So here are frequently asked questions from this session or from this topic. Describe the construction of meter bridge and describe an experiment to find specific resistance of a given wire. So this is about meter bridge. I hope you understood or you learned about meter bridge, which is application of Wheatstone bridge. So with this I am concluding. Thank you so much. So what is the use of meter bridge, or what is the use of constructing a bridge like a Wheatstone bridge, practically known as meter bridge? By using that we can find resistance of an unknown resistant or unknown resistance of a wire, and also we can find the specific resistance or resistivity of that wire by using meter bridge when it is designed in a way like Wheatstone bridge. So that is practical application of Wheatstone bridge. Remember this formula, very important one. Formula for calculating specific resistance is pi r square X by L, where R is radius of the wire, X is its resistance and L is its length. So while doing this practical, or while doing this experiment, we need to take some precautions that only when we are doing experiment we need to switch on the battery, and otherwise we can switch it off. So with this I'm closing. Once again, thank you so much.
Meter bridge, resistance of a wire. The property of a conductor to oppose the flow of charges through it is called its resistance. In this experiment, our aim is to find the resistance of a given wire using a meter bridge and hence determine the specific resistance of its materials. Materials required: a meter bridge, jockey, Leclanché cell, resistance box, galvanometer, key, connecting wires, wire cutter, scale, resistance wire, and sandpaper. Procedure: first, make the connections as shown in the circuit diagram. Take a connecting wire and cut it using a wire cutter. Connect one end of the wire to the positive terminal of the Leclanché cell and the other end to terminal A of the meter bridge. Now take another connecting wire and connect it between the negative terminal of the Leclanché cell and one end of the key. The other end of the key is connected to the terminal B of the meter bridge with another connecting wire. Introduce the resistance box in the gap G1 of the meter bridge. Now, take the resistance wire and connect it in the gap G2 of the meter bridge. Since the resistance of the wire depends on its length, make sure that both ends of the resistance wire just touch on the gap. With other connecting wires, connect the positive terminal of the galvanometer to the central terminal of the meter bridge and negative terminal of the galvanometer to the jockey. Now insert the key and press the jockey B. If the galvanometer deflections are in opposite directions, then the connections are correct. Now, press the jockey almost at the middle of the wire on the meter and introduce a suitable resistance R in the resistance box so that the galvanometer shows zero deflection. Measure the distance L1 from the terminal A to the balancing point. Now, interchange the position of the resistance wire and resistance box in gaps G1 and G2. Measure the distance L2 from the balancing point. Then calculate the mean balancing length L. Then calculate unknown resistance using the equation X is equal to L whole divided by 100 minus L into R. Repeat the experiment for different values of R, and mean value of the resistance X gives the resistance of the wire. Measure the radius R of the wire using a screw gauge. If L be the length of the wire, then the specific resistance of the material of the wire is calculated using the formula rho is equal to pi R square X whole divided by L.
I give you a banana and ask you what's its electrical resistance. What do? You will look at me in a funny way, but then you will remember, Ohm's law. You will say, I'll just hook this up to a battery, calculate the voltage across it, the current flowing through it, and use Ohm's law, right? That's how you can calculate the resistance, isn't it? True, but there's a small problem when it comes to accuracy. You see, in practice, if you want to calculate the values of the voltage and the current, you need to introduce some additional devices in your circuit. And when you do that, their resistances also get introduced in the circuit. And so the values of the voltage and the current slightly changes. And so the resistance will not be exact. It won't be very accurate. So the question is, how do we measure this resistance more accurately? We do this by using something called a meter bridge, which works on the principle of Wheatstone's network. And so in this video, you will see how we can take this meter bridge and calculate the resistance of that banana with more accuracy. But before we get to the meter bridge, let's back up a little bit. What exactly was a Wheatstone's network? Well, a Wheatstone's network is a circuit which looks like this, which there are 4 arms with 4 resistors, and you have a resistor in between. And the whole idea is, if the resistances have the same ratio, like in this example, 1:2, 1:2, then the voltage here and here will be exactly the same, and as a result we'll find no current flowing through this resistor. So the current over here would become 0, provided these are having the same ratio. And it doesn't matter what this resistance value is, or what the value of the battery voltage is, or even the value of the resistors. All that matters is the ratio over here should be exactly equal. Now, if you're wondering why that is the case, then we've talked about this in a previous video called Wheatstone's network. We looked at it logically, and we also looked at how we can extend this whole concept and all the fun stuff over there. So if you need more clarity or a refresher, feel free to go back and watch that video. But our goal is to see how this balanced Wheatstone network is useful in calculating the resistance of that banana more accurately, right? So the way to do is we can use one of these slots and put our banana in one of these slots. So let's say we put our banana somewhere over here. So we put the banana over there. And now the principle is, if you know the values of these 3 resistances, let's say, and imagine you could change the values of these resistances. Okay, let's say they're we call them as variable resistors. Basically, you can change their values. If you could do that, then in principle you could keep changing the values of these resistances until this is an experiment, until you find the current over here to be 0. Does that make sense? You keep doing that until the current over here goes to 0. Now when that happens, you know for sure that this network is balanced, and therefore the ratio of these 2 resistances must be exactly equal to this ratio. And then I can just equate and calculate, because I know the values of these 3. And that's the principle behind the meter bridge. And of course you might ask, how do I know whether the current is going to be 0 over here or not? Practically, how do I know? Well, you put a galvanometer over there. If the galvanometer deflection shows 0, then I know the current is 0. Now you might ask, hey, here also the resistance of galvanometer, won't it screw up with our calculation just like before? No. Before, the resistances mattered because we were calculating values of voltage and current. Those values will change when we introduced, the galvanometer or ammeter or voltmeter. But over here, notice, in this balancing condition, there is no current flowing through the galvanometer, right? So the galvanometer is not even a part of our circuit. And so its resistance won't matter at all. Get that? And even the voltage of the battery won't matter, or the resistance of the battery also won't matter. All that matters is the resistance values of these 3. If you calculate them, if you know their values accurately, you can accurately calculate the value of the resistance of the banana. And that's why this method is more powerful than the previous one. Hopefully this makes sense. And now you might get more excited and say, I'm going to try this at home. But then you start thinking of another problem. Hey, practically, isn't it very tedious to keep changing the values of this resistance and keep looking at the deflection of the galvanometer? How do we do this practically? And that brings us to the construction of meter bridge. So let me take this network and keep it over here. And so the meter bridge consists of 2 L-shaped arms and 1 straight metallic. These are all metals, and these are screws to attach wires over there. And in one of the slot over here, we can attach our banana, whose resistance we need to calculate. And in this slot, we usually attach a resistance whose value is known. This is a fixed resistance. We're not going to change that resistance values at all. And immediately when you compare this with our Wheatstone network, you can kind of see this is our banana. And this resistance now is becoming the resistance of the fixed resistance that we have kept. And now Now the thing to concentrate on is the bottom part. We are not going to add any more resistors over here. Instead, we're going to take a wire which is exactly 1 meter long. It has a uniform area, and you'll see why that has to be required. And we're going to even have a ruler over here, just to show you that this is 1 meter long, and the ruler will also be required later on. And of course we'll have, we'll connect this to our battery, and of course there will be a key over there to switch on and switch off the circuit. And in between this, we will have our galvanometer. And the thing to notice about the galvanometer connection is this side of the galvanometer is not attached to the wire. It's an electrical contact, so there will be some kind of a slider over here with the metallic contact over here, but you can move that. So you can move that slider like this on that particular wire. Now before I continue, can you pause the video and think a little bit about why we need a slider over here and how this part resembles our Wheatstone network? Just pause and wonder a little bit about it before we continue. Okay, hopefully you're given this a thought. So if you look at the bottom part carefully and compared with the Wheatstone's network, you will see now that this part of the wire represents this resistance, this resistor, and this part of the wire represents this resistor. And so as we move the slider, say, towards the right, you immediately see that this wire starts becoming bigger. So let me just switch that. Yeah. As I move this towards the right, this resistance increases because more wire, and this resistance starts decreasing. So notice automatically the ratio of these two resistances keep changing. Does that make sense? And that's how I practically change the ratio of the resistance. And I keep doing that until the galvanometer deflection shows 0. So let me go ahead and do that. Let's say here is our galvanometer. Notice right now it's not pointing to 0. There is some current, which means right now we are not in the balanced condition. So I'm going to move this slider towards the right. Ooh, you can see the galvanometer is coming close to 0. The deflection is going close to 0. Whoops, it overshot. All right, here it is. Now our Wheatstone network is balanced, meaning the ratio of these two resistances must be exactly equal to the ratio of these two parts, the resistances of these two parts of the wire. And so we can now go ahead and calculate it. Before I do that, one thing I would like to know is what's the length of this wire, right? And that's why I have the ruler over there. So with the ruler, I can calculate it. Let's not put a number over here. Let's just call this as L. And so now I can go ahead and say the ratio of these two resistances, which is X divided by R. Let me just write that a little bit at the top. X divided by R. That should equal to, because it's balancing condition, we've reached the balancing condition. That should be equal to the ratio of these two parts of the wire. So this part of the wire, I will say the resistance is RL. I don't know what that is. I'm just going to call it as RL. And this part of the wire, well, if this is L, and I know the whole thing is 1 meter, then I know this has to be 1 minus L. If I keep it in meter. If it's in centimeter, it will be 100 minus L. Let's keep things in meter. So I can now say that this would be divided by resistance of this much length of the wire. Resistance of 1 minus L. Now again, we might run into a problem. I know the value of R, this is known, but how do I calculate the resistance of this wire? That's not given to me. Again, I want you to pause and try this on your own. Think about it. How would you calculate this ratio? How would you calculate the resistance? I'll give you a clue. Think about some connection that you may have learned between the resistance and the length of a material. So, did you remember the relation? The relation was R equals rho into L divided by A, right? So I can use that for this part of the wire. I can also use that for the bottom part of the wire. For the bottom part of the wire, the rho stays the same because it's the same material. Rho is resistivity, only depends on the material and the temperature, which is the same. And so it's the same rho. The length of this part of the wire I know is 1 minus L. This is 1 minus L. And the area of cross section of this part of the wire is also the same as this one. So it's going to be the same value as the one on the top, A. And that's why it's super important that this needs to have uniform thickness. And so now I can cancel this. And notice, all that matters is the lengths. And that is what I'm calculating practically. And I'm done. So from this, I can now rearrange and I can say X, the resistance of the banana, equals R times L. We call this the balancing length. We also sometimes call it the null point because this is the point where there is no current flowing through. So null point divided by, what was that? R into L divided by 1 minus L. And you can do this and you will get your answer. And in short, that's how you can use a meter bridge to find the resistance of an unknown material. So long story short, meter bridge works on the principle of balanced Wheatstone's network. And when the galvanometer shows zero deflection, we know that the ratio of these two resistances must exactly equal the ratio of these two lengths. And why is this superior to the previous method of just using Ohm's law? Well, there, since we are using voltage and current to do the calculation, the resistance of your ammeter and voltmeter screws up or decreases the accuracy. But over here, notice, in the balancing condition, there is no current flowing through the galvanometer at all. So the resistance of the galvanometer won't matter. We're not using voltage or current calculation. All that we're using is the length of the wire and this known resistance. So as long as we do that calculation accurately, we will be able to get a much accurate value of the resistance of that banana.